So our next speaker is Nir Magrata, and he's going to talk about real value somewhat pseudorandom unitaries. Please take it away.
This is joint work with Zvika Borkeski.
So in a paper from 2018, Giulio and Song introduced, as we just heard, two pseudorandom objects, the first being pseudorandom states, and the second being pseudorandom unitaries. I will not reiterate the definitions, we just heard them. Cool. Why are pseudorandom unitaries very interesting? First, they imply many other pseudorandom objects, as we just heard, PRS in particular, also PRSS or versions of PRSS. They also quantum pseudorandom objects are weaker than one-way functions, at least relative to an oracle, which makes them inherently interesting. They're used for benchmarking quantum devices, for quantum supremacy experiments, for efficient estimations of quantum observables. They are also used in quantum learning and in the theory of quantum chaos and quantum gravity. And since the introduction, there have been a plethora of pseudorandom objects, and some of them can be depicted as steps towards building pseudorandom unitaries. But pseudorandom unitaries are inherently more complex than states. Their output is harder to model, and also the variable input is harder to deal with. Some progress towards pseudorandom unitaries was made in specific pseudorandom function-like states, which have classical inputs, and for each classical input output a different quantum state that looks random, pseudorandom isometries, and pseudorandom state scramblers. Other properties of quantum pseudorandom states were also considered. In specific binary phase PRS and subset PRS, which do not use the imaginary part that we can use in quantum states, but still look like random. Scalable pseudorandom states in which the security parameter of the pseudorandom state is independent of the number of qubits, and pseudorandom states with pseudo-entanglement. Our results are non-adaptive orthogonal input pseudorandom unitaries. So let's define it more properly. We have efficient generation. So given a key k, we can construct the unitary uk efficiently, and the unitary is applied on n qubits. And then in distinguishability, let S and T be polynomials, and let psi S and psi 1 to psi S be orthogonal states. Now we want that the distinguisher that makes a query of the following form. We have a T-tensor of each of the orthogonal states, cannot distinguish between the application of the ST tensor of the unitary if it is either from the family or from the random distribution. And we construct such a family using real-valued unitaries. Now I want to have some high-level intuition for why we constructed the unitary as we did. So up until now, many constructions started with an arbitrary state of choosing. Many times it was a uniform superposition over either all of the standard bases or a large subset of the standard bases. Then we randomized the phase, and the output of this process was a pseudorandom state. But now we don't have the same control over the amplitudes of the input vector to the randomization of the phase that we used to have, because now we need to be able to deal with all of the inputs. So we introduce a flattening stage in which we first apply a randomization of the phase F and then the Hadamard transform. And that gets us, after the flattening stage, a state which is flat, in the sense that no one entry is too large. And this is a property that was implicitly used in many other constructions. Finally, we permute the basis elements, which symmetrizes the amplitude. Okay. The flatness follows from concentration bounds, and I won't get into it. This is not the interesting part. And now I'll give a high-level overview of the proof. So we start with this input state, which is just the t-tensor, again, of each state. And these states are pairwise orthogonal. We apply the pseudo-random unitary, or the ST tensor of the unitary, and we get as an output some state. But what are we aiming to? We're aiming for the following density matrix. There is some normalization term, and then we sum over all Z in UST, which means that the inputs, that the entries of the vector do not reoccur, and over sigma in STS, which are just permutations that are local to blocks of size t. Now that we know where we want to get it, let's give a high-level overview of the analysis. So we start with the state. We go through the flattening stage, and we get flat vectors. In general, we can write any density matrix as a coefficient alpha zz prime, and then the entry of the matrix zz prime. Now, because we have flattened the states, this density matrix is close in trace distance, which is the equivalent of statistical distance, to the same matrix, but now only, but now the entries that are not in UST are 0. So we can talk only about the matrix that sums over Z and Z prime from UST. Now we apply a random phase G, which practically removes Z and Z primes for which they have a different entry histogram. Cool. So we get the following representation. We have alpha, Z, and sigma. Now sigma is from all of the permutations over ST elements. Finally, we apply a permutation which symmetrizes the Zs. So we can write the coefficient independent of Z. So we get a matrix that sums over Z and sigma, and the coefficients are not dependent on Z. The only thing left to show now is that nu of sigma is close enough to 0 when sigma is not locally permuting each block of T elements. I'm saying the only thing that is left to show, because this follows from the inner product of the two vectors, of two orthogonal vectors being 0, and the devil is in those exact details. This is the technical part of the proof, and I'm not going to get into it. Intuitively, why is that? Because if we think about sigma that is not local to each block of T elements, it corresponds to an inner product between two input vectors that are input vectors which are orthogonal by the security definition that we gave. Cool. So let's come again to the plethora of pseudorandom objects. And our work lies somewhere here. It's very close to pseudorandom unitaries, but not quite there. Our work also subsumes the works of pseudorandom isometries and function-like states, and partially subsumes the results of pseudorandom state scrambles. partially subsuming because PRSSs are also scalable. In parallel to our work, Madgar, Puemba, Sinha, and Yuen proposed another construction, which is very similar to our construction. The only difference being that the first stage, instead of applying a randomization of the phase and then a random function and and then a Hadamard transform, they used a uniformly chosen Clifford circuit. But their security proof uses different techniques, and they are able to show non-adaptive security. Shortly after, they also showed adaptive security for the same construction. And subsequent works also constructed and proved the security for shallow depth PRUs and PRUs with access to the inverse of the matrix. We could not have gotten even non-adaptive security because in a work from 23 from Hugh, Bardi, and Koch, they proved that pseudorandom unitaries cannot be real. So in a sense, we're almost there, but we have a hard no-go result. What are some future directions that we can look at? Can we prove the security for tensor product inputs? We believe so, and that will give us the maximum security that we can for real-valued unitaries. And in what cases is this definition enough, either orthogonal inputs or tensor product inputs, and what does it say for applications that only use can only use this security definition and do not need to use a full-fledged complex unitary? Thank you.
Thank you for the talk. We have a few minutes for questions.
Hi, thank you for the talk. Do you think there are any particular advantages to having a pseudorandom unitary with real values?
Not that I can think of right now. I think it's inherently interesting, specifically for the second point that I gave. Yeah.
Sure, thanks.
Okay, if not, let's thank the speaker again.